Well, this video is for Math 116, and this is about the second project. So the second project is based on some of the stuff that we did at the end of Chapter 1 on functions and maximum and minimum values. So this one is one of these Pythagorean relationships. You've got this buoy. Ship A is 175 miles due north. Ship B is 150 miles due west. Ship A is traveling due south at 15 miles per hour. Ship B is traveling due east at 20 miles per hour. Okay? So the distance between the ships will be that hypotenuse of that right triangle. Right, represent this side in terms of t, right? Represent this side in terms of t, and then you can say this squared plus this squared equals d squared, where d is going to be the square root of this squared plus this squared. Okay, so that's part A, the distance, right? We want to represent that distance. Sometimes people want to set this up on a coordinate axes. If you do that, be very clear about how the coordinate axes are set up and what the coordinates of those ships are on your coordinate axes. I don't really see the need to set it up that way, but that's the beautiful thing about math, is it's not wrong, okay? I think that this is a much clearer, straightforward way of setting it up, but if you see the coordinate axes method as being clearer and more straightforward, then by all means go ahead and do that, but just be sure to explain it very clearly, okay? All right, so that's part A, is to represent that distance as a function of time. And then in part B, I ask you to, for some calculations. What is this distance at the very beginning when this is 175 and this is 150? What happens after 5 hours? A is going to be going this way, B is going to be going this way. The distance is going to change. What's that going to be? Is it closer or farther apart? How long does it take A to get to the buoy? How long does it take B to get to the buoy? What happens after 24 hours, and are they getting closer together or farther apart? So that's all part B, and that's all going to come from the formula you come up with in part A. All right, part C, I want you to graph your formula from part A, and it's going to look something like this. Let's see here. Positive values of t from 0 to 24 hours. And for D up to 400. So make sure that we can clearly see the graph like that. If you actually make your y minimum 0, frequently you won't be able to see the scale along the axes. And so you can either, in the graph software, on the far right edge of that menu bar, there's like a little hand, and if you activate that, you can drag it away, or you can just set your y minimum to like -50 and your x minimum to like -3, so that you'll be able to see the scale along the axes. What is the closest that the ships come to each other? That's going to be this point right here, where that distance is at a minimum. Okay. What time does that happen? So your t value is going to tell you how many hours. And then you can turn that into a time. We talked about doing that, turning fractional pieces of hours into minutes, hours and minutes. Where is ship A when this happens? So how far has it gone in this direction? Where is ship B when it happens? How far has it gone in that direction? Okay. Let's see. All right, so that's part 1. Take a look at part 2. So in part 2, you're going to have a rectangle where the perimeter is 125 centimeters. express the area of the rectangle as a function of the width. Well, the area is the length times the width. Okay, so take this equation, isolate the length, and then plug it in there. And so now your area will be totally in terms of the width, and we can go ahead and make a graph for that. And in this scenario, you're going to get something like this. We're looking for a maximum area in this case. Okay, so we're going to get this formula, we're going to graph it, and then what? Oh, then we go into the situation where the width is changing. So the width starts out at 5. Let's see, that would make this 115 divided by 2, whatever that is. But it's starting at 5 and it's increasing by 2 centimeters every minute. Express that width as a function of time. So it starts at 5 and it increases by 2 centimeters every minute. So we want some expression, W is going to be some function of time. It should be pretty simple and straightforward. Okay, once you've got that, that's part B. Now once you've got that, take that and plug it in wherever you've got a W in your area formula. Okay, so now we're going to have the area as f of W, then we're going to have an area, I'll use a G function because I've already used f over here, as G of t. So let's see here. So this is going to be W and f of W. And then we're going to have another graph that is similar, but it's going to have some important differences. Okay? So we're going to find this, replace the W's with whatever you get from part B. And then we're going to make another graph, a separate graph. Please don't put them on the same axes. We're going to have a separate graph for the area as a function of time. And then we want to find this maximum point. It should be the same y value in each case, right? Because it's the area of the same rectangle. So what's going to be different, though, is that you're going to get a W value here and a T value here, and that's what I ask you in part D. Explain the relationship between the x-coordinate from this graph and the x-coordinate from this graph, each one corresponding to that same maximum area. Okay, so that's it for project number 2. It's in 2 parts. Each part is 10 points. And as always, if you have questions about it, please let me know. I'm happy to talk to you about it. I enjoy talking about these problems. And if you get stuck, I'll be happy to help you. Thanks.